Hello, everybody. My name's Scott Cody. I came in from Dallas-Fort Worth. I'm an organizer for a meetup in Dallas-Fort Worth called DFW Data Science. Usually I'm the guy organizing the events and not a speaker, but I was fortunate enough due to my background in natural language processing and things of that nature to meet up with I think he's like a really smart guy named Trevor Grant. Unfortunately, Trevor showed me a reboot of the Apache Mahout project where it uses distributed math processing. I was fascinated with his little talk that he gave at my meetup about using eigenimages. He and I collaborated and came up with an even better project. Unfortunately, Trevor is stuck in Chicago with bad weather, so he couldn't make it. His drones didn't get flight clearance to make it here. The plane that they were going to be carried in, that's not going, and they don't have enough big enough battery to make it here either. So it's just me. So I'm going to carry his part of the conversation, and I hope I answer enough of your questions properly. But if you have deeper questions on the math and the Mahout section of the conversation, you can reach out to Trevor at his Twitter handle, which is rockintrevino. I'll show it on the subsequent slides. So with that, I'll get started. This talk is a little bit about Trevor. Trevor is a PMC chair for Apache Mahout and IBM. He's an evangelist. Myself, again, I run DFW Data Science. It's a meetup in Dallas-Fort Worth area. Technically, we meet in Plano, if you know where that is. I work for LucidWorks. I work on the Fusion core team. Most of the time, I'm just writing Java REST API stuff and piddling and twiddling with Solr. So, but I've done some of these things in the past. That's my background. And one other thing, I don't consider myself a data scientist, though I've been doing things that are in data science. And Trevor, he thinks data scientist, the title's already jumped the shark, but he has a lot more flair in his talks than I do. So anyway, so this talk, it is, we have, there's a lot of things that we could be talking about here and doing facial recognition. There's a lot of buzzword bingo that plays in the industry. This is not a talk about deep learning. Deep learning is overused. This is not a talk about deep learning. Deep learning is a good technology, but there are other technologies out there that we can use. Some good old linear algebra. That's where we're going to go. But deep learning, it's got everybody's attention right now. But it's a tool in the tool set, just like a hammer is a tool in the tool set and a screwdriver is a tool in the tool set. You wouldn't try to put a screw in the board with just a hammer. You would use a screwdriver. Just the same thing. So there are appropriate tools. Use the right tool for the job. There's what people perceive data scientists do. Data scientists do everything from the mundane to the interesting stuff. We have all kinds of things people see. But, and one thing I'll say about Trevor he's all about the memes. So you're going to see some kind of flashy stuff in here. It's really interesting. He and I are both super nerds with the whole concepts. But the thing I want to emphasize about deep learning is deep learning takes time. You have to train your models. Those training processes are very expensive. They are time-consuming. You can throw more GPUs at it and make it go faster, but that's money, right? So not everybody has all the money in the world. Not all businesses are Google size, and so we have to come up with other alternatives. I like to say leverage small data to get big effects. So, get a bigger GPU or do less in a smarter way. So here we're going to talk about a different way to do image processing. Say again? Oh, that's from over there. So in this presentation, we're going to do two major concepts of vision processing, image processing. One uses a HAR filter coming from computer vision. That's an open source project. We're going to use that to detect faces. The HAR filter comes with a pre-trained facial recognizer. It uses simple patterns to find faces, but it's not perfect. And then we, in turn, throw that over the wall. Once we've got a rectangle into something to recognize the faces. So again, this is not about neural nets. This is not about throwing data and stirring it around and see what comes out. If it looks right, we're just going to keep moving. The whole point of this is to try to process data as fast as we can, because what we've got is we've got a real-time stream of images coming from a video. We're not looking at stills. We don't have time to sit and wait for the neural net to process, identify a face, and then identify not only that there's a face in the image, but who that person is. So we're going to rely on smaller techniques to get that going. So we just want to go fast and enough of the memes. So, okay. So again, ancient paradigm, fast and cheap. And this is where the hard cascade filter comes into play. So it's, the deep learning's gotten a lot of attention, but R&D, but we're just going to move with other techniques. So cascade filter, all it's doing is it's basically doing either the bit is either populated, light, or dark. There's no grayscales in here. This is a kind of a simplified view of a cascade filter. Again, they are trained to look at different images. You can make a hard cascade filter for a face. You can make one for a dog's face. You can make one for a hand. You can make it for a missile. I come from a Department of Defense background, by the way. I mean, there's a lot of things you can use filters for. The ones that come in OpenCV are pre-trained for faces. So that's a gimme. We can use that for free. So here we have a nice picture, and we're going to trim it to grayscale, and then we're going to find the face in the picture. So here we think we found a face. So this is the hard cascade doing its work. Then, once we have that, we're going to use eigenfaces. Now, in this case, the images, we're going to break them down into 250 by 250 pixels, because the library of faces we're working with are faces from the wild. That's a data set you can download out there. But we're going to decompose images into a series of eigenfaces. You can start off with smaller sets, but we're going to end up with a set of 130 ideal images. That's another word for eigenfaces, by the way. The more generalized term. So eigenfaces deals with just faces, images. Ideal images deals with the bigger concept. So here we are. We have the nice face. We're going to grayscale it again. We're going to pixelize it. We're going to identify the grayscale tones. So here we are. Now we've just got a block. It doesn't look anything like the face, remember? So this is what we had before. So grayscale tones. We're going to assign numbers. And voila. Now we have a vector. So that face just became a vector. That's what I call image compression. I don't know what you guys think that is, but I think this is, awesome stuff. So we just converted a face into a vector, and many faces in turn. The vectors, we stack them up, and now we have an array. So this is linear algebra. We're going to go into using single value decomposition. So you have your matrix of faces, and we're going to arrive at something called the eigenfaces, or the ideal images. So here are the ideal images. Now, a way to think about the ideal images for those in the room that may or may not be familiar with this, think of these as slides on a slide projector. And we can stack these images on top of each other, boost or decrease the magnitude of them to arrive at any face that is presented to us. Now, maybe some of the faces that are presented to us that are not already in the set that we derive the eigenfaces from wouldn't be perfect, but we can get close to it if we have enough eigenfaces and if our training set is large. So that's the premise behind a lot of what's happening here. So we have our eigenfaces. That's the matrix, matrix U. We have the matrix of faces. And then we're using linear combinations of the eigenfaces against U. So going on. New faces come in. We're going to decompose them using the same eigenfaces we created, you could say trained earlier. So we've got a new face, decompose it. It's just a simple regression. And we got that person identified. We can then do things, we can do vector math with that vector. So recap, we got cascade filters. We've got eigenfaces, and there's neural nets and deep learning, which can do both, but you know, we're trying to go fast, and deep learning won't do that for us. So, creating the eigenfaces. This part of the talk is a nod to Trevor. Trevor is he's the expert on using Apache Spark, using Apache Flink. I am a wannabe on it, and I just follow his lead on this part in here. But he's using Apache Spark, Apache Mahout, and why not Apache Spark all the way? Well, Apache Spark will only do the decomposition on a single machine. It doesn't scale out across a distributed network very well. Apache Mahout provides an expression language that's akin to R now. There was a prior version of Apache Mahout where it showed a fellow riding on top of an elephant. They've changed around the Apache project quite a bit, and now it's a very pluggable library. So we've got, under the hood, we've got Apache Spark. It could be Apache Flink in some places. And we're using that to generate our eigenfaces using a distributed network of computers versus using a single node, which is what Apache Spark would do. So, University of Massachusetts face in the wild. The images that are coming in are 250 by 250 pixels. This is why we're using the 250 by 250 array, which results into a vector of 6,500, 200 pixels. So remember, each pixel is a component of the face vector. So Apache Mahout is going to do the computations for us on our faces in the wild, 10,000 of them. Who knows, maybe one of y'all's faces in there too. I don't know. If we had the drones here, we could find out if you look like somebody, one of the faces in the wild. But we don't have the drones here. So OpenCV is going to find the face. Remember, I talked about the Haar cascade filter. It's going to recognize there's a face in the image. It doesn't know who the face is. It's going to try to define a rectangle, and then we're going to use our mathematics and scale the image to 250 by 250 because we're going to normalize, because the whole thing about information ingestion is normalization. So then we decompose, right? Again, this is single value decomposition, or if the face is already there, we're going to use least squares regression. Here we go. We've converted Apollo. That's the name of the character, by the way, from Battlestar Galactica, if you're a Battlestar Galactica fan. So we've converted him into a vector, and now we're going to take him, and we're going to look for him. We're going to take that vector, and we're going to search the database for other vectors that occupy a space near where he is. We're just going to do a nearest neighbor search. So here we go. We got our document. Here's what the query looks like. So if you see, look in there, this is, we've got our magnitudes, E0 through E129. That's our 130 eigenimages, if you will. And a few other bits of metadata about what Apollo, the character Apollo. We're going to use Solr with Scala as our query time. It's a very naive approach in this way, because as you can imagine, a real world database would have enough faces in it that if we had to scan and do a nearest neighbor for every face, well, that's a smoking crater for a data center, right? That's a full table scan if you're a database world. Now, I have to admit, I used to be an Oracle database administrator, and I would just be like this, because that means I'm going to get a big, big box, because this is a problem that has to be solved. It's not like something. But fortunately for my manager, I'm smarter than just doing full table scans every time. So what are we doing? So we were doing nearest neighbor. He's doing the distance function. This is a first cut at this thing. He did it. He's doing it in the Spark engine. So that means that we're doing the comparison from the database and lifting it up and doing the nearest neighbor set outside of the database engine. So we're lifting everything out of the database and bringing it up into memory, and we're doing it outside the database engine. That's horrible, right? but it's naive, but it's a functional thing. It demonstrates the concept. We're trying to do nearest neighbor. So here we go. We got our query response and our documents. We are going to determine via nearest neighbor if this is a new record or an old record. In other words, did this face already exist? If we're close enough, it's the same person. It may not be the same person, but if the distance between the query vector and the vectors we find in the database are nearly zero, well, it's probably the same person. So new or recognized. What is it? So how are we doing this? So the thing is when you're dealing with drones and things like that, they have very little compute capability. Most of them do. But they don't have to be. They could have more horsepower on the machine. The more horsepower you put on the machine, the more compute you can do on the machine. That means that you don't have to do as big a payload. So the drones that we had for our demo, which are unfortunately stuck in Chicago, are very, they're toys. I mean, they're toy drones. They have very little capability in them. So the imaging is being captured from the drones and being shipped live feed to a local machine, which has more horsepower. But the thing is the balance. So are you putting the load on the edge, or are you putting the load on the server? Where is it going to be? So moving on. So the drones, these are the drones that we did. They're very cheap. I mean, the whole thing put together, I think I spent a total of $100 to put this thing together, put together this package. Yeah, it's pretty cool. It runs together. Again, if you have questions about how to set this up, I would strongly recommend talk to Trevor. His Twitter handle is down there at the bottom, and he's actually waiting for tweets right now. So if you guys have any questions for him, you can tweet to him right now. He's online, so he's there. So here's some of the things we run into with this stream of video. You have a lot of things that happen. You have the cascade filters. Sometimes, a lot of times, they recognize something as a face that's not really a face. We call those ghost faces. They might frame the face inconsistently. So like, is the box getting the whole face, or is the box getting part of the face? Maybe it's got just the eyes in the box. So whatever the cascade hard filter picks up, that's what's getting fed in the eigenimage. So, garbage in, garbage out. So you have to try to make sure you try to screen the garbage out as much as you can. Eigenfaces are pretty good, but they can't deal with things unless you plan in advance. So let's say I'm like this. Here I'm frowning. Okay, I'm making a duck face. So, that's going to throw off an eigenimage of me like this, from the DMV. So how do we solve that problem? Well, we can take many pictures of someone's face, do all the faces, and those all go into the training set. One of them will match. So that's a solvable problem, but you just have to plan for it in advance. So the thing about video gives us a lot of latitude. Thing is video in the real world is not Hollywood. So you are not going to have your image suddenly change from my face into a werewolf, or suddenly Abraham Lincoln pops up in the video in frame 5 or something like that, unless you're dealing with make-believe world, right? Now in the real world, in television, sometimes you have some liminal images that show up, but let's not get into that. So we have, the thing is in a video, in frame 1, my face is here, and if I'm walking across the stage like this, well, it's continuous. This is math, continuity. So things don't just suddenly disappear and reappear in the real world. We can count on that. We can bank on that. We can program on that. So OpenCV is going to detect the face in the video frame. It's going to look at the video frame, and it's going to look backwards. It's going to process. It's going to find face. It's going to find something that thinks is a face. It's going to find another face. It's going to keep going, keep chugging, and it's found a series of images that are within a window of time. But, a lot of things can throw it off, as I said, shadows, ghosts, a belt buckle that looks like a face, whatever, it happens. So we've got these things. So one of these does not belong, right? So how do we know? Well, so we can use clustering. So the images have a particular location the rectangles have a particular location within the frame. So we can take the layers of the images and build them up into a cluster and then run a fast clustering process over it to identify which ones belong and which ones don't. Because as I said, your face doesn't suddenly go from here down to the floor. It doesn't just instantaneously do that. You do a fall, but there's going to be frames if the camera's reasonable. Otherwise, you have bad video. So we're going to create windows, and we're going to capture the frames inside the window. So here we go. We see Apollo, and we see the one that doesn't belong, right? Because we were capturing on a frame-by-frame basis the rectangles. And just so I understand what we're talking about for the clustering, it's a one-pass clustering. It's an older technique called Canopy clustering. So Canopy clustering is a really nifty single-pass method. It's kind of old, but it's very effective at identifying things in a flash process. So I would not discard the Canopy cluster out of your tool set. We use the Canopy cluster here to decide where the rectangles belong. The thing about Canopy clustering, it has its own flaws. There's a lot of tuning parameters you have to do. You have to go with loose distance versus tight distance. And these things can cause certain images to coalesce into an incorrect image. So if you're looking at this frame right here, well, in the background you got some faces that are really close to each other. How do we know that that's not the same image? So these are tuning parameters you have to play with. The tight distance and the loose distance. If you have questions about what those parameters are, I would highly recommend the Wikipedia article on Canopy clusters. It does a great job describing the algorithm for a Canopy cluster. So we have adaptive hyperparameters. We got tuning going on. I mean, this is machine learning. It's AI, but it's not neural networks, right? So, and it's fairly effective. So now, how are we going to find this stuff? So we're using, this is my shtick, and that is I'm a database guy by trade. I also run other database technologies as well, but Solr is my favorite, and I'm an employee of LucidWorks, so there's a bit of favoritism right there. Solr is a really good technology for storing data and for doing search. And there's a lot of really neat things that go on inside a Solr database that you can't achieve with a standard relational database like MySQL or Postgres or Oracle. Each of those technologies or tools that can address parts of this in their own way, but I think the Solr one's the best one, so that's why I'm focusing on this. So here again we have Mr. Apollo, or the call sign Apollo. He's identified in the HAR filter, and we've got our document, right? Remember, this is the naive document, the naive query document that Trevor described. But we're going to do some things that are a little bit more agile data science. So this is a play into the agile thing. So what you're seeing right here is the naive approach. We're going to go a little agile. So what do we have here? What I did was, let me go back. So if you notice in this document, we have this is a NoSQL document. We have each and every magnitude or component vector described as a field in this document. We also have metadata describing the actor that we think we found in this document. If I wanted to scale out to beyond 130 component vectors, this metadata down there on the bottom is going to get kind of cluttered out. It's kind of hard to notice. Now, some people care about the clutter in a document, other people don't. I think it matters. Having data compact in a compact human readable way, I think it still matters. That's just my own personal preference. So what are we going to do? We're going to make use of something called term payloads in Solr. So term payloads, what we can do is instead of storing each value in its own field, we're going to munge all the values into one field, and we're going to treat each component vector name as a term. And then we can assign a payload to each one of those terms. That's embedded inside the Solr document. So what you see here is you see the E underscore DPF. This is the dynamic naming convention for Solr documents. And you see the E0 and then a pipe delimiter and then 1.5. That's a magnitude for that thing. And you see the continuing on. So each pipe delimiter is a magnitude. It's the delimiter between the name of the term and the payload assigned to the term. So there's a reason why we're doing this. So if you look, you see the query on the right. What are we doing here? There's some interesting stuff going on here. Do you remember the SolarJ Scala wrapper that Trevor had earlier? So in here, what we've done is we pushed down the nearest neighbor query to inside the Solr database as opposed to running in the Spark engine outside of the Solr database. So now we don't have to ship as much memory. We can do all that inside the power of the Solr server. So the payload function, what that's doing is it's looking for the term eDPF, and then it finds, and it looks for the it looks in the field eDPF, it looks for the term E underscore 00, and then it gets the payload for it. And it's getting the payloads for each and every single one of those terms, and then we're doing a distance function on it. And then we're going to do a sort on that. And this is how we're going to get our nearest neighbor. We're going to take our top 5. So that's why you see the rows equals 5. So I realize there may not be a lot of Solr experts in here, so I'm talking through the query for you. So again, we're doing this inside Solr, not inside the VM of the Spark engine. So, okay, so we've moved the problem out of the Spark engine into Solr. And we're scanning the face. Okay, what have we done? We're still doing a full table scan. That stinks. It still stinks. It's awful. You know, a million faces, and you're going to do a full table scan every single one? I don't think so. This is a cool idea, but this isn't going to run in the wild. Nobody in their right mind would deploy this. I mean, unless it was a small data set of faces. So how are we going to solve that? Let's do a B tree. So how are we going to do this? We're going to do clustering. We're going to come back to clustering again, a hierarchical cluster. So we do a hierarchical cluster of the faces, and we're going to search for the geocenter of each cluster until we find the leaf that we want. And now we can scale. I think this is a lot better. So, and the clustering's tunable. The pixels that you select for the frame are tunable. There's a whole bunch of tunable parameters you can pick here. So again, we're going to go through, I'm going to go through the flow of how this all works. I'm trying to go as fast as I can so we don't run out of time. But you know, Apache Flink gives us a nice API for the streaming. So we're going to get windowing. We're going to window the images coming in on the video. OpenCV detects the faces. Mahout Canopy cluster coalesces the faces and finds the best one. And then you know, keep going, Canopy cluster. There's a lag that's involved in here because every 250 milliseconds, we're going to go look backwards in 2 seconds of frames and find the faces and then Canopy cluster the faces. That's all we have time for. We don't have time to run a neural net during that 250 milliseconds. We don't have time for that. You're going to have a hard reset, so no good. So Canopy cluster is why we're doing that. It's fast, it's effective enough for what we want. So here we go. So we've got our face identified. We're going to throw it in Solr. And how do we do this? So we can take the faces and we can average the faces together and do a lookup. Because remember, we don't have just like one image. We have a collection of images. So how are we going to identify the face? We've got multiple things to choose from. We do averaging. You know, take all the faces in the cluster and smush them all together and then send it in as a query. What do you think about that? I don't know about you. That image, I can't see a face in that image. That's a waste. So this is, it's not going to work. It doesn't work. But it's an attempt, right? So what are we going to do? So the next best approach is to do voting. So we search each face, and we find the ones that match the best, we can store the list, and away we go. Assign the points rank on the distance. So again, eigenfaces over deep learning. How much time would this have taken to do with deep learning? How much GPU would you have had to throw into the mix to make this happen in the time frame we have? So Apache Solr, wonderful database technology. A lot of people don't understand. They think of it as search. They don't think of it as a database. It's a NoSQL database. It's a first-rate database. It scales to petabytes. You can shard. Huge thing. Reddit is a customer of ours. The whole Reddit search used to really stink. It was a lot of people would just complain online. LucidWorks, we redid the search for Reddit, and now it's fast. It's good. I'm a convert. I did not use Reddit because I could never find anything on Reddit, and now I'm a user of Reddit. It scales. It can hold all kinds of data. Solr can hold all kinds of data, and it's great for an agile data development world because it's NoSQL. NoSQL is not the solution for everything, but it holds so many different capabilities. And now Mahout, Mahout is a wonderful technology in of its own right. If you've not been paying attention, it is a expression language for mathematics. That is what it's become. It used to be a bag of libraries. You wanted to do a k-means cluster, well, there was a Mahout routine to do that off of Hadoop. If you want to do a Canopy cluster, you run a Canopy cluster first against your using the Hadoop data set. You get your k, and then you throw that into k-means, and then you've got your clusters. You want to do all kinds of other techniques. It was a bag of tools. They tried to make them compatible with command line tools, but it was hard, and they recognized the problems with it, and they rebooted. And so Apache Mahout is now an expression library. You can plug in Flink, you can plug in Spark. There's other languages that they've made efforts to, but there's no official supporter for Mahout right now. There have been in the past. There's some companies that are dabbling with it, but they're taking like the best pieces of it, moving on. Apache Flink, well, Trevor can talk most about this. I have very little experience with Apache Flink. But what it does is it's good streaming technology, and this is how we get our windows for the clusters, for the Canopy clusters, if you will. So the thing about our drones is this is really not Cylons. If you're familiar with Battlestar Galactica, the Cylons were fairly self-sufficient. They were able to move around fairly independent of each other. But in this case, our drones are really more like the Borg. They're controlled by a hive mind. Without the mind, there's nothing there. So you can think of Solr as kind of like the hive mind. The learning is propagating, it's recognizing the face. The drone found in humans, stuffs it into Solr, and away we go, and it's flying on. Another drone comes along, away we go. Is it the same face or not? The drone knows this much stuff, but that's all it knows. So, this is going to be kind of we think that this is going to be a science fair project in a few years. Your kids will be doing this stuff. This is so close how far we are in this. And so there's a lot of fear out there in the world about facial recognition technology. We made this into an open source project so anybody can download this. No nation state can control this technology. Any one of you can take it and do something with it. We think openness is the key to keeping this stuff clean and simple. So now I'll show you a video of the demo. Let me get over to the video. I'm almost out of time, so. I don't think it's working. Thank you. Yeah, there's no sound to this. So this is the drone, and it's taking video, So you can see the graininess. This is the camera that came with the drone I showed you the pictures of earlier. You can see the OpenCV detecting faces and identifying. This will all be available online for you to pull down. So there's another video. So let's show the other one. Yeah. Yeah. Demo demons.
Oh, the top one.
We already showed that one.
This one.
That's the one we want to show.
Facial detection.
Yeah. So here again, we're seeing the flow of the data going through OpenCV. The windowing is being provided by Flink. Inside the windowing, we've got Apache Mahout doing the Canopy clusters, assembling the frames, doing the eigen lookups against database, and identifying the people inside the images. That's what's going on now. This is, of course, a nice presentation from an Indian channel, but this is, you can see, it's not Battlestar Galactica or anything like that. You can see all the faces being detected and identified. And that's it. That's all there is. That's all I've got. So thank you for listening. You guys any questions? And remind me to repeat the question if I don't do it. So.
How were you able to stream the drone video? You said you were streaming it into a computer or laptop, or
Okay. The question was, how did we stream the video from the drone into the system? So we have the drones have cameras on them. We have in our setup, if you go through, pull down the PowerPoint, we are streaming the video via network into the laptop, and the laptop's in turn doing the processing. So through Wi-Fi connection, yes. Sorry, through Wi-Fi. Any other questions? I will get a link up for it. I'll get Trevor to put up a link for it. So the question was, is there a link for the PowerPoint? I'll make sure that there's a link put up. What are my thoughts with OpenCV and noise function? Reduction. I would say defer that to Mr. Trevor, because that's his expertise. He's the subject matter expert on that part. So I don't. My play in this was the database image lookup on this. So unfortunately, Trevor was stuck with weather. So, but I don't have a lot of knowledge about OpenCV. Go ahead. The question. Say the question one more time. The question was, we didn't take a JPEG and I'm only hearing part of what you're saying. I'm sorry.
You didn't say the JPEG itself is Solr.
No, we can store the what we're storing in Solr is not the raw. The question was, are we storing the raw image in Solr? And the answer is no. We're not storing the raw image. We are making a vectorized representation of the image, an eigenvector. That's what's being stored in Solr. Can we differentiate motion? I'm hearing. I'm sorry. I can't. I'm hearing part of what you're saying. Maybe you can come up. Yeah. I'm sorry. I'm having trouble hearing. Oh, time's up, guys. I'll go outside of the presentation. So.